All right. Good afternoon, everyone. My name is Justin Essery. I'm an associate professor of politics here at Wake Forest University. Welcome to the International Methods Colloquium. The IMC is a periodic, online, interactive seminar discussion on the application of quantitative statistical methodology to the social sciences, sponsored by Wake Forest University and by Springer Publishing. This week's speaker is Magdalena Bennett of the UT Austin McCombs School of Business, giving a talk entitled How Far is Too Far? Generalization of a Regression Discontinuity Design Away from the Cutoff. Magdalena's talk will last between 30 to 40 minutes, after which point we will take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. And you can ask a question at any time, but we will hold all questions to the end unless it's a very brief clarifying question, at which point I can break in and ask that if it's a very brief clarifying question. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box. Otherwise, I will read your question during the Q&A period. A link to Magdalena's slides will be available in the Zoom webinar chat window so that you may refer to it throughout the presentation. And now I'd like to welcome Magdalena Bennett to the IMC. Welcome.
Thank you very much, Justin, and thank you everyone for being virtually here. So today I'm going to be talking about a paper that I wrote last year, which is Generalization of Regression Discontinuity Design Away from the Cutoff. So basically, as most of you might know already, regression discontinuity design is a highly appreciated, I would say, identification strategy in the social sciences because it provides a very clean way that we can identify causal effects. So in this case, for instance, we have a running variable, which is the way that will determine whether units will be assigned into treatment. In this case, above the cutoff, they will be assigned to an intervention, and below the cutoff, they will be assigned to a control group in this case. So one of the main reasons that RDs are such highly evaluated in the causal inference realm is because of its strong internal validity. So under very mild assumptions of continuity across the threshold, we can actually identify a local average treatment effect for those units that are right at the cutoff. One of the main limitations, however, it's its lack of external validity for units that are farther away from that threshold of eligibility. So as we can see here, for instance, there is a clear correlation between the running variable and the outcome that might bias any attempts that we might want to do to actually estimate something that is not just local for that population, which is marginally eligible or not. This basically happens because we have the fundamental problem of causal inference. We have a missing data problem. But in the case of an RD is even more stark because we actually have units perfectly sorted by this running variable in the case of a sharp regression discontinuity design, for instance. And there's actually no overlap in terms of the running variable. So again, we have a set of units that have distinct forcing variable scores at one side and very different running variable scores at the other side. So what can we do in this case? Is there something that we can actually do with this data, for instance, without making sort of heroic assumptions in terms of functional form to estimate something away from the cutoff? And in that sense, what I wanted to explore in this paper is whether we can find a generalization interval. Maybe asking a generalization for the whole population is a very tall ask because, again, these are perfectly sorted by this running variable, so it might be harder to estimate an effect at the ends of the tails of the distribution. But maybe we can find a generalization interval around this cutoff for which we can actually find an effect that is not only local at the cutoff, but more externally valid in that sense. So what I do in this paper is actually identify that generalization interval using additional data and a few extra assumptions and estimate an average treatment effect on the treated for that population within that interval. So the idea here is that I'm going to leverage the fact that I have two intervention periods, a pre-intervention and a post-intervention period. And the pre-intervention period is going to help me inform that generalization bandwidth. I'm going to leverage the use of predictive covariates in this case, to break the link between the running variable and the outcome of interest, or explain away that relationship. So in a similar fashion, such as Angres and Rokanen do on their paper, or Mika Rokanen does on his solo paper as well, and try to enhance this RD in terms of generalizability. And this is basically based on the idea of local randomization near the cutoff. So if we think of a very, very narrow bandwidth right around the cutoff in an RD, we can think that right there, we can get a sort of local randomization. And starting from that point onwards, I'm basically going to gradually start getting away to try to find this generalization bandwidth, depending on how much my variables can explain away that relationship. So some of the main advantages or contributions that I think this method has in comparison to other generalization methods is that, first of all, it's a gradual approach. So there's no need for an all or nothing sort of method. So unlike Angres and Rokanen's method, where they basically have a sample at hand, they run a residual test. If their data passes that test, they're able to generalize for their sample at hand. And if not, they're stuck with the traditional RD. This method is going to start trying to emulate the regression discontinuity design, again, with a very narrow bandwidth, and then slowly start getting away so we can find an interval for which we can generalize for. And that interval is going to be informed by the data, so it doesn't have to be cherry-picked in this case by the researcher. Another important advantage, which comes more from the way that I decide to adjust covariates in this case, is the fact that there will be no extrapolation on population characteristics. So I'm going to be using new methods of matching in this case. That's going to bias the fact that we can keep the units of analysis intact. Each of my intervention units is going to have a counterfactual, and I'm going to be able to compare like to like. Another important thing using this method is that it will make my overlap region of characteristics explicit in this case, which again, I think it's very important, especially when we're talking about a regression discontinuity design, where we have those units perfectly sorted by another covariate, in this case, the running variable. Another, I think, interesting feature of this method is that I'm able to generalize not only for any population of interest within that interval. So not only in this case for the whole treatment population within that generalization interval, but also for instance, for subgroups. So if I want to analyze heterogeneity between groups, I can do it very straightforwardly using the same method. And finally, I don't think I'm going to have time to talk about this, but you can read it in the paper, is the fact that I'm also able to run a very easy sensitivity analysis to hidden bias. So anytime we're doing an observational study and relying on some ignorability assumptions, for instance, in this case, I'm going to talk a little bit about the assumptions that I'm relying on. A sensitivity analysis, I think, is needed in order to see how sensitive our study is to an unobserved bias in this case, and how big should that bias be in order to explain away any effects that we're finding. So I'm going to start briefly talking about basically the generalization, the method itself, GRD, and I'm going to first start with the framework in a kind of agnostic way of how to actually do it in practice. So you can get a feel of what this method is doing without necessarily choosing how we are adjusting for covariates or how we're making other choices in this case. But then I'm going to talk about how I actually do GRD in practice and how some of those adjustment choices, for instance, can bias a lot of nice properties for this method. And then I'm going to briefly talk about an application that I used to demonstrate how this method would work, which is the introduction of free higher education in Chile, and then just end with a few remarks. Okay, so getting now into the method itself, generalized regression discontinuity design, or GRD for short. Basically, what we have here is a two-part problem with both a pre and a post-intervention period. So the main bulk of this problem is actually identifying this generalization interval, which I'm going to call H star. And that is going to be mainly relying on the pre-intervention period data. After I can identify that generalization interval, I'm going to apply it to the post-intervention period and actually estimate the average treatment effect on the treated using the post-intervention data. So I'm going to mainly focus on the first part basically because that's, again, the main bulk of this method, and the part that does most of the heavy lifting in that case. So in terms of setup, I'm going to have two periods, both a pre and a post-intervention period. I'm going to index it by T. And I'm going to have a running variable in this case that's going to perfectly assign treatment. So we're thinking in a context of a sharp regression discontinuity design, though this can be easily adjusted for a fuzzy regression discontinuity design as well. So in this case, units that are below a cutoff C are going to be assigned to treatment, and units that are above that cutoff are going to be assigned to a control group. Again, this is only, of course, in the post-intervention period. In the pre-intervention period, there's actually no treatment. So I'm going to write my potential outcomes basically as a function of both observed characteristics, or predictive covariates, as I'm going to call them, some unobserved confounders, and also the running variable. So I'm going to separate, again, the running variables from this predictive covariates, because, again, I'm not going to use those running variable as an adjustment. And I'm going to have an additive treatment effect in this case, but I'm going to allow that treatment effect to also vary by characteristics, both observed and unobserved. And finally, I'm also going to allow it to be just a natural growth from period to period, which is basically that period fixed effect. So in this function, basically, we have, this is the setup, right? The solid lines will be what I can actually observe, and the dashed lines, what I can't. So as you can see, the pre-intervention period, I can observe everyone under control, both at the left and at the right side of the cutoff. While in the post-intervention period, I can only observe units under treatment at the left side of the cutoff, and units under control at the right side of the cutoff. So again, I'm going to have a missing data problem. And basically, what this whole method is going to be about is trying to create a solid counterfactual for this potential outcomes under control for the treated side. So this is basically what I'm going to do, and I'm going to use the pre-intervention period to help me with that. So the idea here is that I can actually write my potential outcomes, my conditional expectation of the potential outcomes, conditional on the running variable, which is basically, again, the same functions that we were seeing here in this plot. And what I want to do basically is, using the pre-intervention period, is identify an interval h. And again, this doesn't have to be a unique interval. There's actually many intervals that can comply with this restriction. But the main issue is that the main gist of this intervals h is that I can express the running variable as a function of observed characteristics, or predictive covariates in this case, that vector of variables x, and some random noise. So again, you can think about this if the running variable, for instance, is income, maybe in some sort of interval h, where it's not that big of a difference between the running variable. If I control by education, for instance, I can break the link between the running variable and whatever outcome of interest I have. So that's the main idea with finding these generalization intervals. And again, you can think about this in the limit as being the very most narrow bandwidth around the cutoff, and maybe just expanding it a little bit until I get the maximum or the widest generalization interval that I can. And in that case, what I'm going to be interested in actually is that widest generalization interval. So I'm going to call H star the widest generalization interval on the treatment side in this case, basically because that will be representing the largest portion of the treated units. So if this H star exists, which again doesn't necessarily need to exist, because it could perfectly be that I don't have covariates that are predictive enough to actually comply with this restriction, or maybe my running variable is just too well correlated with the outcome and I just can't break that correlation. But if that H star actually exists, and again, in the limit, you can think about that H star as being the most narrow bandwidth around the cutoff, then that means that within that bandwidth, if I condition by a set of observable characteristics, then the potential outcomes in any two of those points, it's going to be the same, independent of the value of the running variable. So what does this mean actually graphically? Because I think it's a way easier to understand when we look at it in a plot. So the idea here is that I want to try to flatten those potential outcomes. So what I'm doing is that by conditioning on this predicted covariance, I'm explaining away the relationship between the outcome and the running variable. So this is what I have here. I have my potential outcomes conditional on the running variable adjusted by the predicted covariance x. And basically that breaks the relationship between the outcome and running variable. And I am able to flatten within this h star my potential outcomes. So basically so far, everything I've done is just using data that I have at hand, and I haven't made really any great assumptions about how this behaves. But the issue here is that I'm actually not interested in this generalization interval for the pre-intervention period, but I'm actually interested on this generalization interval for using it in the post-intervention period. So here basically comes the assumption that I need to have in order to be able to do that transfer. So the main assumption that I'm going to be relying on in this case is what I call the conditional time invariance assumption under control. So basically what this means is that the conditional potential outcomes under treatment in the pre-intervention period will follow the same trend as the pre-intervention, as the post-intervention potential outcomes adjusted by those covariates as well again in the post-intervention period. So this sounds a lot sort of like a diff and diff assumption, and to a certain extent it is. I'm assuming actually that there's no change in unobserved confounders between the pre and the post-intervention period within that generalization bandwidth. But basically this differs from the traditional diff and diff assumption in two ways, I think. The first one is that we're only focusing on that generalization interval. So we actually do not care what's going on outside this bandwidth. If the tails are changing differentially or unobserved confounders are playing a role there, it doesn't really affect our analysis. And the second one is that we're actually leveraging the fact that we have an RD. So we're going to be able to partially test this, at least for the control side on the post-intervention period, because we can actually observe those units. So the idea is to see whether I can actually flatten those units and that potential outcome in the control side on the post-intervention period while when I adjust for those predicted covariates. And this is basically what it's going to look like. Now we're in the post-intervention period. Again, we're applying the same generalization interval H star. We will try to, ideally, we want to flatten those potential outcomes under control, which is the red bar, the red line here. But the good thing is that we can actually observe this and we can see whether those are flattened or not. If they're not flattened, then maybe there's some unobserved confounding that's going on, and it's not a good idea to use that as a solid contrafactual for the left side in this case, so this one. But if they're flattened, basically that gives me a certain a robustness test to assume that maybe on the left side, I can also flatten them, and that could be actually a solid counterfactual. So that basically what this leaves me is with the different treatment effects at different points of the running variable in the treatment side. So that's what we're gonna actually try to identify. So how do we do this actually in practice? So before I start talking about the method itself, I just thought that I would talk just very briefly about the adjustment method that I will be using, which is representative template matching. So basically representative template matching, what it does, it takes a mini version of whatever population of interest we want to make inference on. In this case, for instance, it will be the treated group on the post-intervention period. And we get a representative template sample, or template for short, and it's going to be a mini version of that population. So the idea here is that we want to match multiple groups at the same time and get a set not only necessarily of 2 units, but maybe 4, 20, or whatever the number is that we need for matching. And that is actually a very difficult problem computationally to solve. So what representative template matching does is that we will match each of these groups, for instance, treatment in the pre-intervention period, control in the pre-intervention period, et cetera, to this template. And because they're matched to the same unit, by construction, they're also going to be matched to each other. So this is like a clever way to bypass that idea of matching more than 2 units, which again, it's a very difficult optimization problem, and just leveraging the fact that we can do pairwise matching really well, and then just by construction, merge everyone afterwards. So this is the idea that this is basically the main way that I'm going to be adjusting for covariates in this case. And the way that I apply GRD in this case is going to be a recursive sort of method. So I'm going to go through this in a bit more detail, especially showing the plots. But the main idea here is that I'm going to start with a very narrow bandwidth, again, trying to recreate that traditional regression discontinuity with that randomization inference sort of narrow bandwidth around the cutoff. Then I'm going to select a template within that, that narrow bandwidth, and I'm going to match all units in the pre-intervention period to that template. I'm going to fit a local polynomial, which again, it's going to be sort of the way that I'm going to recreate those conditional potential outcomes under control in the pre-intervention period. And I'm going to find that section where those potential outcomes are actually flattened. Then I'm going to update my generalization bandwidth. If the template region is smaller than the generalization bandwidth, I'm going to do everything again, expanding a little bit the template again. And I'm going to do it until basically both the template region and the generalization interval intersect. And if they intersect, then I have basically the widest generalization interval that I can. How does this look actually in practice? So again, I started with my post-intervention period because I'm interested in those specific characteristics. So I'm going to identify the narrow bandwidth following Cattaneo and co-authors method. And I'm going to select a template for the treatment side of that bandwidth. This will basically give me a template of the characteristics that I want to emulate on the pre-intervention period. So I'm going to take that template and I'm going to, in the pre-intervention period now, match each of these bins within a grid to that template. So basically, again, I'm creating a sample with different values of the running variable, but within those values, they have basically the same distribution of characteristics. So again, it's a way of conditioning in the adjusting by those covariates in the conditional potential outcomes. So I start with the narrowest, with the bandwidth closest to the cutoff, and I match those units, and then I match the next bin and the next one, and so forth until basically I've matched everything that I can. So basically, as you can see here, I have no matches here or here, and that basically is because I have no overlap of my characteristics. So this is what I was talking about when I was saying that this will make actually explicit where I have actually overlap in terms of other predicted covariates. So my generalization interval will be at most, best case scenario, as large as that overlap region. I can't go any further because if I want to go any further, I would have to extrapolate in characteristics, which is something that I don't want to do. So great. We found that overlap region. So then what I do is fit just a local polynomial and see where I can actually find that flattened region. So if we take only the matched observations and use that to match this local polynomial, as you can see, we get something that it starts kind of increasing, then it flattens out, and then it increases again. This basically means that at the ends of this, I can't really explain away that correlation between the outcome and the running variables using the predictive covariates that I have, but I can for a region there. So that will be my new generalization interval in this case for this iteration. So then what I need to ask basically is whether this is the optimal one that I want to obtain. And as you can see, the template region, basically the population that we're generalizing for, which is this population right here, the gray area, is much smaller than the actual generalization interval. So this means that I can probably go farther away from the cutoff. I don't need to be confined to just that small narrow bandwidth. So because the generalization interval is larger than the template region, what I'm going to do is actually expand the template. So I'm going to go again to the post-intervention period, go farther away from the cutoff, select a new template, the same size, and just do this all over again. And I'm going to do this all over again until the template region and that generalization bandwidth actually intersect. So in this case, I've reached the optimum of this algorithm, and where basically I can't expand my template region any further without not being able to explain that correlation between outcome and running variable. So I will stop here, and that will be my H star. So if you can see this, basically this can break in two ways. The first one is if I have no overlapping covariates. So as you could see from one of the plots, there's just ends of this distribution where I can't actually match because I don't have populations that are similar enough to my template. And the other one is that the predicted covariates don't actually explain the correlation between H and R and the running variable and the outcome. So this is basically what we're doing just in an animation. So again, we start with a small narrow bandwidth. We identify our first generalization interval, and then we're expanding the template region and moving again, re-identifying our generalization bandwidth in each iteration until we get that convergence between both. Usually the generalization interval is going to be getting narrower on the control side because again, I'm using more representative sample of the treatment side. So that again will make probably a shift and making it narrower on the control side. After that, actually is very easy way to do this, the estimation of the average treatment effect for that region. And what I basically do is just take that template that is representative of my H star interval and use it to match both the treatment and the control side in the post-intervention period within that bandwidth. And because, again, I have a matched sample, it's a very straightforward estimation given this setup. For instance, you can think that you can do a pair t-test or a Wilkinson pair t-test. And the fact that you're using pairs, again, also will help reduce, make your confidence intervals narrower. So you can also take advantage of that. So in this case, for instance, in a pair t-test, what we're doing is basically running a sort of a difference estimation in terms of differences in potential outcome, in observed outcome, sorry, in the pre and the post-intervention period. As you can see, we're using here a difference in the pre-intervention period outcomes, and that by construction, because the way that we build actually the generalization interval, that will be very close to zero. So it will actually not impact that much the point estimate, but it will introduce a little bit more variance for the confidence interval. So it's going to be affecting that side. Basically, this is to incorporate the fact that we don't have a perfect zero, but we're estimating sort of that difference. So let's move now to the application of free higher education. How do we actually do this in practice? So just to give you a brief context of higher education in Chile, we have a centralized admission system, which actually works through a deferred admission mechanism. Students basically take Chilean SAT, which is the PSU, and they have their admission score, which is a weighted average or both of their PSU score, their GPA, and their high school ranking. With that admission score, they apply to different colleges and programs within colleges. They have 10 preferences, for instance, and they rank them, and they get admitted or not, depending on how they're sorted by their admission score. Before 2016, which is the year when free higher education was introduced, the financial aid package looked basically was composed by both scholarships given by the government and universities, and also government-backed loans. So students could go to private banks actually and get backed by the government in order to take those loans. The free higher education policy was introduced in December 2015. So Chile is in the southern hemisphere, so the academic year goes from March to December. And it was introduced basically at the very last moment that it could be added to the budget. So it was kind of unanticipated. Students had already taken the PSU, but they hadn't applied to college yet. And in order to be eligible for this program, you had to belong to the lower 50% of the income distribution. And also you had to be admitted to an eligible program, which was basically all the programs that participated in the centralized admission system. So again, this did not necessarily help you get into college, but if you got into college, it gave you a free ride. So it was a very a good deal for a lot of students that were more vulnerable. So what I wanted to study here was what was the effect of actually being eligible for free higher education on both application and enrollment to university. So in this case, I'm going to take as the treatment as being socioeconomically eligible for free higher education. So you can think about this as an intention to treat in terms of free higher education. And I'm going to be looking at both application to university and actual enrollment, because there's a lot of students that apply but don't end up enrolling for different reasons, especially if they're in the lower portion of the income distribution. And this is basically because I want to see whether lower income students, for instance, have more financial constraints, and this might help them basically finance college. However, for those students that are targeted for this introduction of free higher education, there were already available a lot of scholarships and for those first 5 deciles. So it looked more like kind of like a shift of one financial aid package to another that was kind of similar. But where it could differ was in the saliency of the policy. So before you had a lot of different scholarships and everything had different eligibility criteria. So you had to be quite well informed to know whether you were eligible for each of these different scholarships. But this one was just one big policy. So you knew that if you were in the bottom 50%, that you were eligible for this. So that saliency might also have affected students differentially, especially those that did not have so much information about higher education. So what I want to see actually, if there is actually larger effects for those students that are away from the cutoff on the lower side of the income distribution. And I'm going to be comparing traditional regression discontinuity designs with my GRD results. What data do I have? I have 3 cohorts, 2014, 2015, and 2016. 2015 and 2016 are the 2 years I'm going to be using for the analysis itself. But 2014 and 2015 also lends itself very nicely to run placebo tests. So that's also a good feature of this. I have very rich baseline data, demographic and socioeconomic data at the student level. I have their standardized test scores in high school, different school characteristics. I also have complete application data in terms of what score they got in each subject, whether they applied and where they applied, and also whether they end up enrolling or not. So this is basically what the RD looks like. In the pre-intervention period, this is great. We don't see anything at that cutoff, which is a good sign. And in the post-intervention period, in enrollment, you can see there's a clear jump at the threshold of eligibility, which again kind of indicates that there's something going on with the eligibility criteria in this case. So for implementing GRD, there's certain choices that we need to make. We select a template size of 1,000, which is basically the size of is the number of units that are within that very narrow bandwidth that we're going to start with. So that basically sets up the size of our template. Given also that size of the template, I'm basically dividing my data into 20 bin grids so that I have roughly 2,000 units within each bin. And I'm going to be doing mixed integer programming matching, which again is just a way to balance covariates directly. I'm going to balance just by the mean on variables that I think are not that predictive necessarily. So like academic performance, some school characteristics, and some demographic and socioeconomic variables that are not as highly as important as others. And I'm going to do also fine balance, which basically means that I'm going to be balancing the categorical distribution of these covariates, which I think are most likely more important in this case to break that link. In this case, it's going to be gender, parental education, and also their different scores.
Multiple flags to everyone.
With all this setup and reproducing again the GRD, I get a generalization interval of minus 500,000 pesos to the treatment side and 300,000 pesos to the control side. So that's going to be the generalization interval that I'm going to be using for the post-intervention period. So if we look at the data, this is basically the same RD plot that I had before, a little bit zoomed in this case. This will be the gray area, is the generalization interval, the population that I'm going to be able to generalize for. So in this case, again, it's not the whole population. I'm missing very much the bottom, which basically I'm missing because I cannot match those characteristics to the treatment side, which again is not surprising given that they're perfectly sorted by income. But that still is 50% of my treatment units, which is, I think, a lot compared to what we would get just using a traditional RD. So I'm going to be able to generalize for at least the kind of the top 50% in terms of income of the treatment students. I can also do this robustness test for the time invariance on the control side for the post-intervention period. So basically this is looking a little bit at this, at this after adjusting for the covariates that I had. And as you can see, it's pretty much flat, at least for that, at least for this section, right? So this gives me a bit more, gives my assumption of time invariance a little bit more bite, because I can see that at least for a section of this distribution, I am actually able to flatten this, this potential outcomes. So just to quickly look at the balance for the entire sample, basically this is the absolute standardized difference in means. So the farther away they are from the y-axis, the more unbalanced these covariates are. And it's not surprising to see that they're very unbalanced between the treatment and the control group. Again, they are basically perfectly sorted by income, so big gaps is not really surprising. If we look at the units within the generalization interval before matching, we can see that still there's some important differences. So for instance, especially like in standardized test scores and things like that, and even mother's education, there's some important gaps that we would need to adjust for. So that's actually what we do after we match. And as you can see, we can take most of those differences down to 0. And again, that is basically buying us the fact that we're flattening those potential outcomes. Okay, so we have two groups that are very well balanced, at least in observable characteristics. We're assuming that there's no time invariance, so we can go ahead and get our results. So this is both the left panel is going to be the following just a robust RD for both application and enrollment, and the right side panel is going to be the generalized regression discontinuity design, again, for both application and enrollment. So focusing in application, we can see that actually the RD is just marginally not statistically significant at conventional levels. It's like the p-value is like 11%. So the idea here is that we have a slightly smaller effect for the RD and a larger, slightly larger effect for the GRD, which is 5.2 percentage points. Again, because of the confidence interval, I cannot reject that these are actually the same. But as you can see, at least the point estimate seems to be growing. We can see a similar story actually for enrollment. And I guess that most of the action is going on in enrollment. Okay, so basically students did increase their application, but most importantly, they did increase also their enrollment rates if they were eligible in this case for free higher education. And it does seem that this effect is kind of increasing as we move farther away from the cutoff. So again, I cannot reject that this is actually increasing because of the size of the confidence interval. I cannot say that this is actually increasing because of the size of the confidence interval, but at least it shows a tendency to increase in terms of point estimates. So just finally to finish up, I just wanted to reiterate some of the main points of this method. And the first one is the fact that GRD is a gradual approach. So again, it's not all or nothing. Worst case scenario, you're left back with your traditional regression discontinuity design. But in most cases, you can get a little bit farther away from that, which is, I think, a good solution. We're going to use data to inform that generalization interval. So again, there's no need to cherry pick which one is going to be the interval that we're going to be using, which I think is also an interesting feature because it doesn't rely so much in the discretion of the researcher. The use of matching avoids extrapolation, and I think it has some nice properties, both again in the sensitivity analysis realm and also to make explicit that overlap region. Some of the limitations, of course, is that we do need more data. This cannot necessarily be applied directly to a traditional RD. You do need a pre-intervention period data. And we do have to rely on that conditional time invariance assumption for the post-intervention period. However, as I showed, we can run a partial robustness test, at least for the control side in the post-intervention period, which I think gives this assumption a bit more bite if it passes that robustness test. And just finally, I wanted to end up with some extensions and just some motivation for this. Actually, there's a lot of settings where you can think that you have sort of a difference in difference RD sort of situation, which is what we need for this setup, such as geographic RDs. So there's, I think, a lot of ways that we can actually apply this method. And again, it might not be the perfect solution in terms of generalizing for an entire population, but that I think is a tall ask from this type of data and how it's generated. But at least it gives us an idea on how we can actually get farther away from that cutoff and not just rely on that very local estimate that is provided by a regression discontinuity. So thank you. I have the old version of the paper, but the new version is coming very, very soon. And it's going to be available also on my website. The old version is also available there if you want to check that out as well. Thank you.
Thanks, Magdalena, for that presentation. At this point, Magdalena Bennett is available to take questions from the audience. You can ask a question using the Zoom Q&A button that appears at the bottom of your webinar window. If you wish to be recognized and ask your question via audio, please indicate this in the Q&A text box. Otherwise, I will read your question during the Q&A period. And we've got a couple of questions that have already come in, both from an anonymous attendee. Is representative template matching similar to propensity scoring? Are they the same tool?
Not necessarily. So basically, let me go just back to... So basically, representative template matching is a bit agnostic in the sense of what matching tool you use. You could potentially do it with propensity score matching. I don't, and basically the main problem with propensity score matching is that it doesn't necessarily assure you a balance in the sample at hand. So in expectation, it will balance your covariates if you have like a lot of repeated, if you do it like infinite times. But we want to actually ensure certain balance and balance covariates directly. So in this case, this is done with mixed integer programming matching, which is, again, balancing basically covariates directly. And also one of the important things here is that usually when you want to match more than 2 units, so for instance, 3, what usually people used to do was just match 2 first, then average those units, and then match the average to the third one, right? So then you get a match set of 3. So you were doing pairwise matching, but you were losing a lot of information when you did that first averaging. So in the end, your match sets didn't necessarily look the same because you were losing information in each of these kind of iterations. So representative template matching sort of bypasses that, and even more if you think about doing this with something that balances covariates directly, such as integer programming matching, and not necessarily something like propensity scores.
The next question is also from an anonymous attendee, maybe the same one, I don't know. Just to clarify, why can't we use the generalization bandwidth as the bandwidth in a traditional RD analysis? I think what they're asking is, you get some bandwidth in RD.
Mhm.
You are widening that bandwidth after adjustment. Why can't we use that wider bandwidth in a traditional RD analysis?
Okay. If I get the question correctly, basically it's comparing what you would get with an optimal bandwidth with a traditional RD and this bandwidth.
I think so.
That's actually that's a very good question, and it gives me a good time to actually clarify this. They're actually two very different things. So for the optimal bandwidth in a traditional RD, what you're doing is basically taking what units you're going to be using for estimating that RD. But that RD, again, is only for those people that are right at the cutoff. Again, if you think about this asymptotically, you're going to be fitting some sort of function that, again, can be in the RD robust. It's going to be like a local polynomial, and you're going to be using those units within that bandwidth. But again, that jump and that effect that you're estimating is just for those at the cutoff, even though you're using more units, clearly, because you cannot just use the probably 2 units that you have right there at the cutoff. This generalization interval is different in the sense that we are actually estimating for that population. So in an RD, even though you have an optimal bandwidth, you're not really generalizing for that population. You're still just getting an estimate for that at the cutoff. And in this case, the generalization bandwidth is actually doing it for that population that is within that bandwidth and not just that jump at the discontinuity.
I'm going to ask a couple of questions that I had, and they might be stupid questions, but that's fine because that will help clarify what's going on, even if they are dumb. The first question I have is there's a paper, I think it's actually a couple of papers, that talk about thinking about matching as a pre-processing algorithm. And you essentially can do matching on a sample and then do analysis on that sample later after the matching, and that procedure is doubly robust because if the matching worked, you'll get good answers, and if your parametric model or whatever worked, you'll still get good answers. Why don't we just match on the entire data set between treatment and control cases and then do an RD, right? So in other words, why don't we try to make the sample sort of broadly equal and then do an RD on what's left?
Yeah. First of all, I really think that there's no dumb questions. And actually, I think that that's a very good question. I would say that the first limitation of doing that is that one, you will not be able to match everyone, as we saw in the application, for instance. There's clearly parts of the distribution that it will just like break, right? You just don't have enough overlap of characteristics. You clearly don't have overlap in the running variable. So you will not be able to match that. The second thing I think is that even though you can match, for instance, in the overlap region, you will get very well-matched samples in terms of observable characteristics. But again, then the unobservables come into play in that sense. And you can think of 2 units, for instance, in the case of the free higher education. You can think of 2 students that have an income, for instance, of $75,000 and $100,000 household income, right? And if you adjust for all the other covariates, they maybe don't look that different afterwards. But that, I think it's a harder ask if you have a student that has, like, I don't know, $25,000 income in your household. And even though you adjust for all the observable covariates, comparing it to someone that has, I don't know, $150,000 in income, clearly there's something unobservable that needs to explain that huge gap in income that you're not necessarily accounting for. So if you were going to do that matching, basically most of the weight then it's going to be basically transferred to whatever parametric or functional form assumption you make in that sense. And I think
you're still doing an RDD afterward, though, right? So you still get the cutoff and the quasi-randomization.
Ah, okay. So you're meaning just matching and then doing an. Oh, okay.
Yeah. What I'm to clarify: take the whole sample, match the whole thing, and then run an RDD.
Ah, okay. Yes. That's interesting. I actually had not heard about that. I mean, you will still be with the traditional stuck with a traditional sort of local average treatment
Sure.
effect in both cases. And you would expect, I would think, that both of them did not necessarily change that much. If they do change a lot, then that means that probably in the traditional RD before matching, maybe your functional form was doing a lot of the.
Well, I'm not surprised you haven't heard of it because I just came up with it just now, based on what I had read earlier. And I mean, I think the trade-off would be you're going to lose data. You already mentioned that, right? But your bandwidth might be bigger because the cases are more comparable. And
That's true,
so the sort of the question is, which is better? And is it better to use your sort of RD first and then match, or match and then RD? I don't actually know.
Yeah, I think that's a good question. I think it has kind of trade-offs. Theoretically, I would say that they're the same because again, you're assuming that right at the cutoff, there's no differences between both people, right? But in practice, you are using data beyond the threshold to estimate that, so that can generate differences. Yeah. So there will be, I guess, efficiency and like, again, that variance bias trade-off in that sense. But I would expect if the traditional RD was kind of well done, they should be fairly the same in that sense.
So another, I don't know if this is an opposite question or not, but you say the point of this procedure is to sort of flatten the relationship between the running variable and the outcome in the pretreatment data, right? Because the idea is essentially you want the RV to be unrelated to Y.
Yeah.
I mean, the best way I know how to do that is to run a non-parametric regression on RV and Y, and then extract the fitted values, and what you have left is going to be guaranteed to be noise, right? Mm-hmm. Why don't we do that instead of doing the matching thing?
Basically because the idea of using the matching is that I am trying to use the additional information that I have from predicted covariates to try to explain that away. So if I run just a traditional, I mean, I guess you could run a regression with the running variable and some covariates, because you need to have some covariates, right? And do that. I guess that would also work. And it's not necessarily, it doesn't go against sort of the framework part that I showed. I do think that matching sort of buys us this additional settings, but you can think that you can adjust in different ways. It doesn't necessarily need to be matching. So in that sense, you could do the method that you propose. I just think that matching sort of buys us this additional very sort of cool properties that I use a lot, specifically also in terms of sensitivity analysis that I didn't get to present here, but I think it gives us more robustness in our study in that sense. But you can absolutely use other adjustment methods in the same framework.
Well, I don't see any other questions from the audience, so I'm going to thank Magdalena for being our presenter this week. I want to remind everyone that her presentation will be posted to our website just after the broadcast if you want to share it with a colleague or watch it again. I also want to tell you about next week's talk. On March 19th, we're going to host a talk by Cameron Wimpy of the University of Arkansas. He is giving a talk entitled On the Interpretation and Application of Spatial Regression Models in Political Science. Please see our website, www.methods-colloquium.com, to get more information about this talk. Magdalena, thanks very much for being here today.
Thank you very much.
And I hope to see everyone next week.